PhD student at KIT, and we will present you wireless networks in the loop. So that's basically the idea comes from Martin. So from a time when he was my advisor at the lab, and so we've implemented.
Okay, yeah. And I'm Gerald. I was also a student with, and Martin was my advisor when I did my master thesis. So yeah, and that's why I also worked on this project. Okay.
So first about the idea about wireless networks in the loop. So SDR simplifies radio development. Well, I think you all know it's not true for everything. So there come new problems and so on. But the great thing about this that we can apply our workflow, which we know from software development, for the workflow of radio development. So there are debugging tools, automated test and test-driven development. And the idea or the question to answer is, why just use them for a single block or a single node? We could use them for the entire network, so to simulate the entire network with all nodes and the channel in between them. This would be great if we could allow seamless switching so that we can work with the same code base for our real application, which we run on the USRPs or other SDR hardware, as well as for our simulation. So that we could improve in every single iteration, where we can switch when we switch from testing or real-world measurements to simulation. So the main idea is to stay in the software domain as long as possible and to go back into the software domain as soon as possible if we have to do real-world measurements. The benefits of this approach are for sure flexibility and scalability. If you want to test really big networks like 20 or 30 nodes and you want to get a feeling about how the network will behave in this case, for most labs or for most people it will not be possible in real world with real hardware. The other benefit is that we have only one code base. So you don't need a MATLAB simulation code, or you don't need to run NS3 simulations right before. You could. Yeah, it's depending on how complex your network will be, but you don't need to. So a great benefit, I think the greatest benefit of it is the easy debugging. So the possibility to set breakpoints on the air link is really nice if you develop complex networks, and also the controllable realism. So you can turn on and off impairments. So everyone knows that it's easy to run a simulation on the PC without something hardware or real-world impairments or something like that. And here you have the option to turn on the hardware impairments, but not so the channel impairments. And this all leads to a reduced development time and an increased feel-good factor. So I come to the basic principles and implementation. So we've chosen a client-server structure so that you could run really computational expensive tasks like the channel simulation on a powerful server, and you also could run several PCs as single nodes and connect them to the server as you would do with hardware setup. So you have 5 laptops, each with a USRP equipped, and the real channel is then simulated by our server and the samples go there over TCP/IP. So here are some points that we had to implement. So first of all is zero padding, which I came through in a minute, and then all over the timing is a really problem when you want to simulate a channel. So the easiest question is, what do you do if the node stops sending, if your application stops sending? What would you do in a simulation? Because if one node stops transmitting, all of the other nodes still get noise in a real time and in a real environment. So you have to simulate it, and the big problem about this is that you have to get the exactly correct amount of samples which are noise samples. So we had to implement something like timed commands or support for timed commands, which you would use in a USRP to enable it to transmit at several times, or if you have a hopping scheme. We also have support for an absolute time with it's the model of the GPSDU or the support for GPS time. Then clearly there are the hardware and the channel models. So we have different channel models and all of them are modular designed, so you can easily add new ones. And last but not least, there's a simulation interface. Because to allow seamless switching, you don't want write different code for the simulation, because you want to use the same code as we would run in our real simulation to allow the switching between the measurement and the simulation. So let's come to the zero padding in detail. When you run slotted, if you run slotted applications with the USRP, one possibility is to use the start of burst, timestamp and end of burst feature. It's called stream tags in GNU Radio, or it uses stream tags from GNU Radio. And the idea is that you could count the number of zeros you have to insert here, because you know the start of burst and a timestamp. Then you know how much samples go through your simulation. Then you have an end of burst, and with the next timestamps you can calculate this difference. And you know this amount of samples, and then you can add this one. The problem is that you know this one not at this moment. So you don't know how much samples you have to add here. So we implemented a method that starts producing noise or zeros or anything and distributes them to all the receivers, and until it gets a timestamp. Then it calculates how much it had produced already and how much it has to in the future. And if it produced too much, it gives you a warning and error and says, stop, here's a simulation error. So then you have to run the simulation a bit slower. So we have implemented three versions. It's the sample accurate zero padding, which I explained right now, and generic inaccurate zero padding. What this does is it simply waits, and if there's nothing on the input of the work function, it produces noise. And there's also the initial zero padding, which is important if you have transceiver systems which whose output depends on the input. So there's a chicken egg problem at the beginning. When there's no input, the transceiver produces no output at the end. So therefore we implemented an initial zero padding which produces noise at the start if the work function don't get an input. So we followed overall a modular design to allow you to easily add channel models, hardware models, or change everything in between them. And also the simulation interface could be changed. Right now we are using TCP UDP things in GNU Radio because they're well known and they're working good, but you really easily could exchange them. So in the past we used Twisted for the exchange of samples, but that didn't perform well, so we just use it for signaling now. And yeah, as you can see here, the switching is really seamless. So the blocks have the same options, so because I copy pasted it from the UHD blocks and add some of the simulation parameters to it. So there's support for existing applications. So in my master's thesis I wanted to show the performance of the overall system with some PER and BER curves, and therefore I used the standards TX benchmark RX, which are part of the GR digital package, and it worked out of the box. So I simply I took out the UHD block and added a WinAllow source block, and it worked out of the box. So another important task is to provide status information like the UHD does. So at which frequency are we now, at which sample rate are we? And also gives support for the application to change the frequency and such things. Therefore, I've created a frequency hopping ad hoc application, which is quiet which has great possibilities for failures when you want to simulate it, because you have to model this, the mixing between the frequencies, and the overall ad hoc is really depends on doesn't behave very well if you fail, or if you have failures in your overall or in your simulation or your channel model. So as you can see here, the differences right now are you don't see the DC offset, which would be very easily to implement, or the RX filter characteristic, which is implemented already, and yes, the data packet and the interferer at 340 MHz. That's also an opportunity to push interferers into the whole simulation. So to test your network if in the presence of an interferer, or perhaps in the presence of secondary user, primary user, when you think about cognitive radios. So I want to show you a demo now. So what you can see here is the frequency hopping ad hoc application. So at the left there's one node which has addressed itself dynamically, and also the second node, so they have two addresses. This one has address 1 and this one address 2, and when I'm able to transmit packages from 1 to 2 like this, or from 2 to 1 like this. And this is a real application which also runs on a USRP, so I've tested it, and what I've done here is I've taken out the UHD block and inserted the Vinilo block. So, and we can have a look at it. So that's another feature, we can easily connect new applications to the simulation server. So now I connect a simple Qt GUI sync. So the server's running here on the left. You can see that it makes some new connections. And then we could maximize this. So now the overall flow graph stops, and there it runs, because we needed the initial 0 padding here for the overall application and simulation to start. So and here you can see a beacon package, and so I could transmit some packages so that you can see that it's really this application running here. So here are the packages. So, and that's one possible workflow, so it helped me a lot when I developed this frequency hopping ad hoc node, because there's so many possibilities to make failures, and it's easily to debug with a framework like this. So, and now Gerald will continue.
I'm going to talk a little bit about channel models here, because so far we talked about the whole setup, how the system is working with the server, the centralized server, and the nodes that connect to the server and exchange IQ samples, but we completely disregarded so far the channel models. Okay, and I think because most of you are computer science guys, so maybe I give just a rough and quick introduction and what the problem is if for an engineer who does wireless communication when he's trying to transmit data over the air. Okay, so the problem is that our wireless channel, which we are using to transmit data, behaves very differently, and it depends on various factors. So of course it depends on the frequency band. So whether you're transmitting at 100 megahertz or at 2.4 gigahertz, makes a lot of difference. Or for example, if you're outdoors or indoors, that's also a huge difference. How long does it take for your signal to get from the transmitter to the receiver? That's just one example. It also depends on your movement speed. So if you're talking on your cell phone, if you're moving around on foot, or if you're driving in a car, you also have to take that into account. Other thing, it also depends, for example, on the data rate. If the symbols that you're transmitting are very short, and therefore you can't transmit a lot of data, or if they're long, it also makes a difference. I'm getting, I explain it in more details later. And it also depends, of course, on the position of objects. If you're surrounded by tall buildings, or if you're just in a free space somewhere out in a forest or something. Okay, so here is a very simple scenario. We've got our base station, we've got our cell phone, and then we've got, of course, a line of sight path correctly, but we also have multiple paths which are, well, rescattered by, for example, forest buildings or whatever. And all of those paths, they have different delays because they are differently long. And then all of them also have a different phase. So, well, they can either add up constructively or you can have interference depending on the phase, which changes your signal level that you actually receive. Moving the receiver, well, it also, if you walk around, for example, with your cell, then you change, you also suffer from interference. I don't know, probably all of you were in high school and you know the double slit experiment. So there you have this maxima and minima on your wall, and well, that's the same thing that you suffer on with, if you suffer from if you have a cell phone. And moving also affects the perceived carrier frequency at your receiver. You also suffer from a Doppler shift. You also have to correct that. So that's just some of the tasks that you have to deal with. So, and now then, instead of a flat line for your received power, for example, you get something like this with these drops in between, and that's just called fading. And well, it depends, of course, if you move around. And well, in the talk of Tom earlier, you saw that he had this nice little example where you had the signal, the sine signal, and then he also added interference. And if the interference gets too big, then you can't hear anything. This pretty much is the same, just the other way around. Your useful signal, the level drops, and then you don't receive any. You do not receive anything, just rubbish. And well, of course, fading. Well, it depends on the movement speed. So how fast does it change, for example, or also of the position from all the transmitter or the receiver. So if you're out on the street and then a large truck moves in front of you, then of course you're more or less covered, and maybe on your signal level drops. Okay, and then of course you also, if you make a general model, you have to take your environment in which you are communicating, has to take that into effect. Okay, so one thing about channels, they're described by the channel impulse response. Or that's just one way to describe them, and it's very simple. Imagine we have a transmitter and we are transmitting a short pulse, and then the receiver, depending on how many paths we have, you'll get probably maybe something like this one. So this is our first path that we receive, and then a little bit later with a little bit detail the other paths. Okay, so and this is what we actually call the channel impulse response, and that you can you have to keep that in mind if you want to design your system. Okay. So, just as an example why the channel impulse response is so important, well, in both cases we have the same channel impulse response, with it's these short pulses over here. And now imagine we are transmitting with a very low rate channel, with a low data rate. So this example would be our transmitted signal or symbol, so let's say just 1 bit. And of course we receive it on all paths, but we can see they all add up, because they are very short, they are very long in time. Now we're transmitting with a load and with a higher data rate, so our pulses are, of course, they are shorter, or our symbols are shorter. And the first symbol is the red one, then the green one, then the blue one, and then the magenta one. We can see we're now transmitting the magenta one. We also get interference from the other paths, but with other symbols. Here we just receive the blue one, there we get the red one. So, and this phenomenon is called inter-symbol interference, and that's the reason why we actually need equalizers in our system, which is what Martin already mentioned. So, as you can see, well, this is the same channel, but just because we're using a different system, we also have to adapt the channel model, and have to adapt our system. So this is why channel models are so important. And now what we wanted to do is wanted to not just create channel models which you can do analytically, make just some reflections about the environment that you're expecting, but you can also sound the channel, which means measuring the channel impulse response, which itself describes the channel. This is called channel sounding, and the easiest way is, well, you transmit a short pulse, and then you detect all the echoes that you're receiving, and then you pretty much get the channel impulse. Problem is, you're just transmitting very shortly, most of the time nothing, so that's not very efficient because well, your signal to noise ratio is very low. It's smarter to transmit all the time. So the idea is the correlation channel sounder, and it transmits a sequence repeatedly, and then these sequences have now very nice properties. So if you use the autocorrelation function on them, then they've got this large peak when they are perfectly aligned, but if they're shifted a little bit, then they are close to zero. So, and this is when we now transmit our this sequence at the receiver, at the transmitter, then we can use this correlation to detect the different peaks on the and then we can detect the different peaks at the receiver. Okay. So, and then I can just show a couple of pictures. So what we did, we made some measurements over here. So we placed the transmitter, and thanks to the buildings we'll get multiple, we'll get this multi-path environment, so we'll get different, well, we can actually detect different paths. And just maybe this is of interest to you, this was our setup. So we had the transmitter, we had the receiver, and we just hooked them up to two laptops. Which actually ran the processing radio. We also had GPS disciplined oscillators, which you need to measure the Doppler shifts of the multipath components. Okay. Yeah, I have to speed up a little. So this then, for example, the results that you get. So if you're moving around, this is actually what your received power. And as you can see, it fluctuates quite a lot. And here, we've got the power delay profile, which is kind of the time average of the channel impulse response. And as you can see, well, here we've got a line of sight peaks at the beginning, and then those are the paths that we receive from the buildings, and then over there we get nothing. That's just nice over here. Okay, and then from these measurements, then we can also make a channel model. I think I skipped the demo due to the time. But now the question is, well, what kind of models can we use in clean radio? So you can make some very simple analytical models like the WHEN channels where you just add noise, or Rayleigh fading channel, or we also implemented COS207 channel models which were used for designing GSM. But the design of wireless networks in the loop, you can, on the server, is basically running a clean radio flow graph, which simulates the channel. And so you can plug in pretty much any GNU radio block as a channel model. And as of 3.7, there's a project called GR Channels from Tim O'Shea. And, well, he implemented a couple of channel models, which you can also use.
So Tim's channels are now part of GNU radio?
3.7, yeah.
Yeah.
I think
I
mentioned it. Okay.
Yeah, we probably did.
Yeah, okay. And well, as a kind of experimental feature, you can also create channel models from channel sounder measurements. So if you don't want to think too hard about the environment and don't have an analytical model around, you can just use a channel model sounder measurement and then take from that one, create a channel model. Well, but this is still very basic. And I think I leave the last 2 minutes for what outlook or what we want to do in future. Well, there have been a lot of new features lately, so we have to clean up our code base, and we want to release it at some point in 2014 to the public, so then you can get it. And well, Nico is currently working on powerline communication, so he also wants to add some new channel models for powerline communications. And he's also working on this graphical user interface for managing the whole application. So, yeah, this is what we are currently working on. And now we've got time for questions, or if there are none, we can. Okay, no, yes.
Are there models useful for HF?
HF of these models, honestly, I don't know. I've never worked with HF. I think that's 13 megahertz or something.
That's ionospheric, it's all different kinds of
Uh,
communication.
No, then definitely not. Because, well, you have to take into account the ionosphere and troposphere, and, well, that's...
Those models are not designed.
No, so AWGN just adds noise, and really it's just basically when you've got completely surrounded by scatterers, which is not the case in, well, HF.
So we try to provide a framework or to build up a framework, so there are really simple models in there up to now. But as I heard before, so Bastian had the same or a similar idea, so I think we have to push it as soon as possible to work together on the whole thing and not to have 5 different radio simulation tools or channel sounding tools.
Okay. You said that you use a GPS deal for synchronization of different hosts. Do you also simulate the drift of the local clocks of receiver and sender?
Basically, the function of those GPS DOs is that you don't have any frequency offset at the channel sounder. You mean, but you're trying, if you're simulating the same aspect in our hardware model?
No, I mean, if you simulate it, do you have also take into account that the oscillators of sender and receiver drift apart? They're not running the same frequency. That they start to drift.
No, currently not really. Well, it depends on the hardware model. You can pretty much plug in any hardware model, but since we are in the infancy of the project yet, we just add a little bit of noise.
But there is a GNU radio channel block that does the drifting. I'm pretty sure about that. Yeah, you can add the drift. So the idea with the hardware is that they would resync. Usually there's pulse per second input, so you constantly resyncing to the GPS signal for one thing.
Okay.
I mean, just one by the oscillator input from there. So plus or minus reality, you're within pretty good spec. Like the two are going to be pretty much locked together based on that. And then you have your other hardware or your channel models that you add your own frequency drift to. We now have it where it's dynamic, or your timing offset works, which can be dynamic now as well. And then we also have the hardware impairments model, which we use to simulate IIP3, IIP2, phase noise, quantization noise, those types of things as well to try to model the hardware getting into it.
Yeah, but just an example. This is, for example, now. Actually, we are plugged in the channel model, and now we are sounding the channel model. And well, this is basically how the channel impulse response is changing. But it can happen from the Doppler frequency, but you can also say, well, it's happening as we saw that the oscillators are drifting apart. That's the reason why in the channel sounder we use those GPS DOs. We wanted to measure the Doppler shift, but you have to know, well, do you have the shift based on the Doppler or because the oscillators are drifting apart?
Okay, so you use that as a reference oscillator, so you have a stable signal, stable frequency.
Yeah.
Okay.
If you want to simulate bad hardware, that is possible.
Perhaps the last question.
Yes. Yeah, one more.
Yeah.
Sorry.
So kind of.
For the cost writing 107 model, you run on environment to say it's GSM that it's mobile or it's countryside?
So you're asking about the cost 207 channel models. Okay, basically there are 4 propagation environments. I think there's one for typical urban, then bad urban, hilly terrain, and rural area. So you have those 4 channel models, and then depending on what kind of simulation you want to run, then you can plug in one of these.
Are you then select inside I want urban and
Yeah, exactly. Okay, then
perhaps we can together so after the presentation, so to get some ideas from you who are developers for software-defined radios, what one could need or what we could implement with this tool. Yes, thanks.
Okay, thank you very much.
let's do that.